So maybe I need to give a heads up, a short introduction just in case. Yeah.
Yes, yeah, that would be very
okay.
helpful.
So Gerald, have you started recording?
Yes, I started the recording
great.
now.
So Max graduated from a world-renowned group in Yale, which is Michel Devereux group, which is considered one of the leading superconducting qubit group in the world. And he then moved to Professor Will Oliver's group as a postdoc, which I just visited last week. So as I said, what Max is about to talk about today is a little bit different. It's a special type of qubit called the Andreev spin qubit. Basically, it's a little bit connected to the condensed matter physics. In the normal transform, we have a capacitor and the Josephson junction. We kind of solve the charging energy, inductive energy, then form the two-level system. In this case, they use the RF square, which has a loop and the weak link. So basically, effective circuit is a inductor and the junction capacitor and the Josephson junction. So the whole Hamiltonian, you can still do the math, and in the end, it's sort of become a level, it's an Andreev-qubit level, so which you can still consider as a two-level system, and it's inductively coupled to the resonator, which is he's going to talk about today. What I found interesting is that, I'm also new to this field. I knew this because we have a mutual friend called Vala. At that time, we kind of write a proposal together. He introduced a lot of Max work to me, and I'm interested in how this work can impact the development of the superconducting qubit, because I'm not familiar, so I want to know the sort of advantage of it. On the other hand, I do know there's a parity switching time that this system can start, which is related to the Majorana bound state, because we want to operate the Majorana bound state before the quasiparticle poisoning take place, and this parity switching time is related to the quasiparticle poisoning. So let's thanks Max to give this talk, and you can get started. Thanks, Max. Yeah.
Thank you for the kind introduction and the summary. That was a great summary of what I'll tell you about. Okay, let's see if I can get back to PowerPoint. Okay, so you can still see my PowerPoint, right? And now it's full screen?
Yeah, it's full screen.
Great.
Yes, yeah.
Okay. I come from I did this work for my PhD when I was part of the superconducting qubit group of Michel Devereux. So I'm used to, I think I do think about this work from the point of view of somebody who thinks about superconducting qubits, but it does have different flavors of condensed matter. So this image that you're looking at here in the background is an illustration of the kind of central device that this work was done on. And you can see my mouse, right? We're gonna get a laser pointer. Let's see.
Yeah, I can.
Options, visible. Okay. I'll just use the mouse. So this thing running down the diagonal of the screen is a nanowire. So the width of this is about 50 nanometers, and it's made of two different materials. So the green material is a semiconductor. It's indium arsenide in this case in these experiments, and then the blue material is a superconductor. And so you can see that we have this structure that's superconductor, semiconductor, superconductor. So this is indeed a kind of Josephson junction. So what we're doing in this work is we're trapping a quasiparticle of the system in the Josephson junction inside here, and then we use its spin as a qubit. And this is what we call the Andreev spin qubit. So that's what I'll be telling you about today. But before I get into the details, I want to start with superconductors and semiconductors separately, and then how we can use them. So as I'm sure many of you know, superconductors, their central property is that there's some kind of electron pairing, and this causes all the electrons to pair up into the condensate. And this condensate can carry current without dissipating energy. And in our modern world, probably the most ubiquitous use of superconductors is in nuclear magnetic resonance, in MRI, where we use these materials to generate large magnetic fields in order to image our bodies, such as with this machine here. But then maybe a little closer to home for us physicists, this is one of my favorite examples, are these kinetic inductance detectors, where we make circuits out of superconductors, and then when high energy particles, such as alpha particles or beta particles, hit the circuit, they break part of the superconductivity and shift the resonant frequency of the circuit. Now, on the other side, we have these semiconductors, and probably the most important effects of semiconductors is this field effect, and this lets us control the flow of electrons through them in very precise ways. But then in some semiconductors, and this is going to be important for what I talk about today, there's also a spin-orbit coupling, coupling spin and momentum, and they can also have enhanced interaction with magnetic fields. And so the field effect, of course, is critical to all of our devices in classical computing. But then there are other fields such as spintronics, where we use spin-orbit coupling in order to control the flow of spin through devices instead of the flow of charge. So in this work, we're going to be focusing on these heterostructures known as superconductor, semiconductor, and nanowires. And so here's an image of one of these nanowires here. You can again see that it's about 50 nanometers across, and it can be several microns long. And if you look at a hexagonal cross-section, or if you look at a cross-section of this thing, you can see the nanowire is actually hexagonal, and then on two sides of this hexagon, the superconductor has been deposited. Now, if you zoom in on the interface between the superconductor and the semiconductor, so here the semiconductor again is indium arsenide, and the superconductor is aluminum, you can see that the crystal order of the materials persists all the way up to the interface. These little dots here that you're looking at are actually the atoms in the material. And because this order is so perfect, it means that the electrons that are moving in this material, they get hot back and forth between the superconductor, the aluminum, and the semiconductor, the indium arsenide. And in this way, they can kind of pick up all of these effects at the same time. They can have pairing, but they can also experience the field effects, spin-orbit coupling, and enhanced G factors. And in terms of applications, there are many. So, for example, these nanowires have been used to investigate, as we discussed before, some aspects of topological superconductivity. Basically, by applying a magnetic field along the nanowire, you can create, or it's thought you can create, and there is a good bit of debate in this field, but it's thought you can create 1D topological superconductors that have Majoranas at the end of the nanowire, and then you could potentially use these to build certain kinds of quantum computers called topological quantum computers. You can also potentially use them to make Cooper pair splitters, where individual Cooper pairs in the superconductor are split into two different paths, but they remain entangled. So it can be a kind of entanglement generation. And then finally, the work that is most close to what I'm going to talk about today is that if you make Josephson junctions out of these nanowires, then they can have very rich spectra. And we wanted to use this to our advantage. So the question we set out to investigate was, with these heterostructures, what kind of new quantum control can we achieve? Is there some kind of new qubit we can build out of them? I didn't say this at the beginning, but please, if anybody has any questions at any point, please just interrupt me. I'm more than happy to stop talking and discuss. So before I get into how we actually use these nanowires to make new qubits, I want to talk a little bit about, just to give you some more context, how quantum information is typically done using superconductors and semiconductors separately. So on the superconducting side, and it sounds like there's some people maybe in the audience that are experts in this, we typically work with superconducting circuits where we're working with trillions of electrons in a superconducting condensate. So in this image that I'm showing here, this is a depiction of a transbond qubit. And the transbond really just consists of a capacitor pad. That's these big blue pieces of metal here and here. And they're connected to each other via Josephson junction, which I'm illustrating here with this cartoon schematic. And the idea is just that the trillions of electrons that are stored in the condensate, they can slosh back and forth from one capacitor pad to another, going through the Josephson junction in a quantum mechanical way. And information can be stored in this anharmonic oscillation. And so one great thing about superconducting qubits is that they're relatively big, and that means they're easier to interact with. Now, on the semiconductor side of things, people typically work at a totally different scale. Instead they work with, instead of trillions of electrons, individual electrons are trapped in quantum dots, such as in this device here. Here, the green is the semiconductor, and the gray are electrostatic gates that people use to trap the electrons. So typically in these devices, people are working with, say, 1 to 3 electrons. And then once they have these electrons trapped, they store information in the spin direction and use the spin as a qubit. And one advantage of these semiconducting qubits is that they're relatively small. which makes them harder to interact with, but it also means they're relatively isolated from their environment. And in some cases, they can have quite good coherence times, in particular, pretty good Q1 times. So in our work, we wanted to combine basically these two approaches into the Andreev spin qubit. And before I get into more details of how this qubit actually works, I do want to give credit to the theorists. It was originally proposed back in 2003, and then there's been several theoretical works on this idea since then. So here's the center of our device. Basically, this is an image of the nanowire of our device, and the key thing again is this nanowire that's running down the center of the image. And again, you can see that there's superconductor on the left part of the nanowire, superconductor on the right, but then in the middle here, we've etched away part of the superconductor to leave only the semiconductor behind. We also have some electrostatic gates. I'm not going to talk too much more about them, but I do want to emphasize that they're actually for maximizing transmission through the structure, not for confinement. So we're not making a quantum dot in the structure directly. These things over here are leads that connect to the rest of the circuit. I'll explain what the rest of the circuit is in a little bit. So imagine we have a quasiparticle sitting in the superconductor. So it turns out that in all of our superconducting circuits, basically in transons or whatever else we might be working with, these non-equilibrium quasiparticles are quite prevalent, and they're just kind of all over the device. So in this example, let's say we have one sitting out on the left lead here. And then let's imagine what the potential energy landscape for this quasiparticle looks like as a function of the direction x along the nanowire. So on the y-axis of this plot, we have the excitation energy, and then x-axis again is again the nanowire region. So on the left and on the right, we have this superconducting pairing. And so in this blue region here, due to this pairing, there's a potential energy gap. And so the quasiparticle can't exist below this energy gap. There are no states here for it to occupy. And this is the same over on the right in the other lead. But in the middle, where there's only the semiconductor, there is no pairing. So what we end up with is a finite square well looking structure. And this is really very similar to the finite square well that you learned about in your first quantum courses. And what can happen to this quasiparticle is it can fall in and get trapped in the bound states that form in this finite square well. And the Andreev levels, really all they are the bound states of this finite square well. So in this work, we're going to be focusing on primarily two levels. There'll be a couple more levels that we'll get into, but these are the most important two. And they're the spin up and spin down states of a quasiparticle that's trapped in the junction. And these two states form our qubit. This is what we call the Andreev spin qubit. So there are two questions that we kind of needed to answer, needed to show that we could do in order to say that we were actually using this degree of freedom as a qubit. And so the first one that we investigated was, can we actually detect the quasiparticle spin? So this basically means, can we detect which of these two states is this quasiparticle occupying? After that, we moved on to the second question of, can we coherently manipulate this quasiparticle spin and therefore use it as a qubit?
I want to add a little point here. So basically, this is the already spin splitted, single entry bound state. There should be one positive, one negative, but you are talking about just one of the level which is already spin split.
Yes, that's a good point. It's already spin split, and I will get into the details of how that spin splitting happens. But they're in this. So I'm also using this is definitely a detail for the experts. But in this picture that I'm using right here, this representation of the Andreev levels, it's known as the excitation picture of superconductivity. And in this picture, there are no states below 0. So there are no negative energy states. There are only positive energy states.
Okay.
And I'll be using that. It's basically what it is in the excitation picture. We're referencing all of our energy levels above the energy of the superconducting condensate. And I'll keep doing that for the rest of the talk. But yeah, definitely happy to talk about the pictures of superconductivity if you're interested.
Okay.
Yeah, so this is my outline for the rest of the talk. I'll go into more detail on this qubit. I'll tell you about how we detect the spin, manipulate it, and then if we have some time at the end still, I'll tell you about. So this work is a couple of years old now, and so there's been a couple other exciting developments performed by other groups around the world that I want to tell you about if there's time at the end. So I just gave you this analogy that it's really like a finite square well, this junction. And if that's the case, then why? What's so special about it? Why don't we just use a quantum dot? And to understand what's different, really, there's a critical difference. Let's first consider the case of electrostatic confinement. So again, we can imagine we have some 1D system with electrons, and again, we have this finite square well-looking picture. But now I want you to imagine that the potential energy barrier here is set by maybe electrostatic gates or something. So this is a normal potential energy that you might be used to. Now, in this situation, it turns out we can actually calculate the bound states that'll form in this well by considering the following picture. So imagine we have an electron moving to the right. Once it hits this barrier, it'll undergo a reflection process, turn into an electron moving to the left. That electron will get reflected back into a right-moving electron. And if all the phases that these particles pick up during this process constructively interfere, if they add up to a multiple 2 pi, then a bound state forms. And it turns out you can actually use this to calculate the energies of the typical finite square well. Now, with superconducting confinement, we have a very similar picture, but there's a critical difference, which is that when the electrons hit the barrier and bounce off, they don't get reflected as an electron, they instead get reflected as a hole. And this is a process known as Andreev reflection. So once this electron gets Andreev reflected into a hole, this hole can travel back and get Andreev reflected again back into an electron. And then we have a similar story. If the phases accrued in this process add up to a multiple of 2 pi, then again, a bound state can form. But this level is quite special, because if you look at it closely, you can see that in this Andreev reflection process, charge isn't actually conserved, because we have minus E going in and then plus E coming out. So that 2E of charge has to go somewhere, and it turns out that it's getting injected into the superconductor in the form of Cooper pairs. So there's basically a pair of electrons traveling to the right and a pair of holes traveling to the left. And this is happening kind of continuously. So actually this bound state is transporting supercurrent through the junction. And this is the critical difference, and it's really what gives the Andreev spin qubit its edge. Because in this case, in the case of electrostatic confinement, an electron in the structure is totally confined. It's totally confined to this dot, and it's difficult to communicate with it because it's so small. But on the right, even though the level is localized to the junction, the supercurrent that it carries can flow over much larger distance scales. And we can use this supercurrent to actually couple to other Andreev spin qubits, to resonators, to other kinds of qubits. This is really the powerful tool that we're going to use in order to manipulate this qubit. So the level structure of the Andreev spin qubit can be kind of qualitatively derived, I'll say, by considering the fact that we can actually imagine 4 different kinds of loops like this. So we can have, for instance, this yellow loop is what I already showed you. It has electrons moving to the right, and they have spin up. We could also have electrons moving to the right with spin down. That's the purple loop. But then we could also have spin up and down electrons moving to the left. So basically 2 directions of travel, 2 directions of spin, 4 kinds of loops total. And if we consider the energies of these things, if we haven't really done anything to the system, if we haven't biased it or thought of other material qualities, then the excitation energy associated with these 4 states is going to be equal, basically. And this is basically just coming from spin and momentum degeneracy. So we have these 4 degenerate levels, but in order to use it as a qubit, we need to split this degeneracy somehow. And so the first thing we're going to add is a spin orbit coupling. And what this does is it makes it so that certain of these loops carrying certain spins move faster than the other 2. And because they move faster, that's actually going to result in them moving up to higher energies. So the yellow and teal loops are now at higher energy, and the pink and purple loops are at lower energy. So this is due to spin orbit coupling. So this is one critical property of the semiconductor that must be there for this to work. And then the second thing that we need to do is we need to embed the junction in a superconducting loop. That's this blue box here. And then the current carried by these Andreev levels is going to travel around this loop. And then when we thread a superconducting flux through this loop, it's going to phase bias the junction, and it's going to break this degeneracy. Basically because the pink and purple loops, for example, carry current in equal and opposite directions, and they couple to the flux bias like this. The current, basically the Hamiltonian term, is just the current times the flux. Because the current is in equal and opposite directions, the pink level moves up by a certain amount, and the purple level moves down. So this is what we can use to get our spin splitting. And this is kind of necessary. We need to be able to break the degeneracy between the 2 spin states so that we can manipulate them.
I want to ask a question here because I
Yeah,
do
please.
read your work starting with the 2018 PRL. At that time, you
Yeah.
don't have this kind of. I mean, at that time you have the entry level qubit instead of the spin start to play
Yeah.
a role.
Yes.
What's
Exactly.
the difference?
Exactly.
What's the difference between this
So,
early paper
yeah.
and
Sure.
yeah?
So the difference is so this is a great question. So there are two. I wasn't gonna go into too much detail, but I'm happy to talk about it. There are basically two different kinds of Andreev qubits. There's this Andreev spin qubit, which we were the first to demonstrate. But then we also worked on this other kind of qubit called the Andreev level qubit.
Yeah.
And the central difference in the Andreev level qubit is that we don't need to break the spin degeneracy, first of all. So imagine we just had a situation that looked like this in our Andreev levels. It is possible the condensate exists down here at zero energy. It is possible to send in radiation that is equal to the energy of this level plus the energy of this level, and basically coherently break, Cooper pair, and put an excitation into this level and this level at the same time, and use that as a qubit. So it's kind of like the qubit in that situation is whether the system is in the ground state, so no excitations, or whether both of these levels are occupied at the same time. So it's basically that qubit operates in the opposite parity sector. The Andreev spin qubit operates in the odd parity sector, where you have an odd number of excitations in the system, whereas the pair qubits operate in the even parity sector, where there is an even number of excitations in the system.
So to introduce this spin degeneracy, to leave this spin degeneracy in this system, what different thing you did in this science paper? Because system is the same, but
yes. Okay. So what's interesting with the pair qubit is that you can't always tell if you actually have a spin splitting or not, because you're only looking at the energy of this level plus this level. And you can imagine that if I shift the pink level down and the purple level up from the point of view by the same amount, by the point of view of that transition, that joint transition, there's no way to tell that it's actually spin split. So even in our 2018 work, it could have been the case that it was spin split, but it's not necessary for it to be spin split. And the device was a little different. So really the central difference between the device is that the device I'm talking about now has a longer semiconducting region. And this is you'll notice I had this little asterisk up here in the upper right. This is for a non-zero length junction. And this is important because basically the length of the junction, the longer the length of the junction, the longer the distance over which the spin orbit coupling can act. And actually results in a larger kind of splitting between these two sets of levels, this splitting here. And so this splitting is, so I think that's the bigger difference probably between our work on the level, the pair qubit and spin qubit.
Okay, yeah. While the junction is longer, you still
the junction is longer.
But you still want to have the short junction limit, so you have just one conducting channel.
The short. Yeah, well, there's two, and you can kind of imagine two different dimensions to the nanowire. There's the width, and the width of the nanowire determines a little more the number of conduction channels in the system. And then there's the length. So short is good from the point of view of transparency. Like you want your electrons to have a high probability of making it through the semiconducting region without undergoing scattering. And if you make the junction too long, then that probability goes down. So in this work where we tried to hit a sweet spot of having a long enough junction that spin orbit coupling could act, but not too long, not so long that the scattering would become a problem.
Okay. Thanks. Yeah, that's good. Sure. Yeah, that's good. Yeah, thank you.
Sorry, may I ask a question about more? Yeah. So the spin orbital coupling is introduced remove the degeneracy of the original the four, right? The four,
yes,
like the same situation right here. So can you give a little bit more like a quantitative number saying that by introducing this spin orbital coupling, how large is these like in the right hand plot right here? How large is the energy splitting that you can generate that over there?
Yeah.
Because it seems to me that if the size of your nanowire or this gap right here is not precisely controlled, actually maybe you're falling into a region such that it's pretty hard to control these levels as the qubits. Yeah,
it's true. It's true. So to give everybody a sense of the absolute energy scale here, this delta, I don't know.
Yeah.
So I come from a superconducting qubit background, so I think of this energy in gigahertz. This is 44 gigahertz roughly.
Okay.
So a typical transmon is like 5 gigahertz or so. So let's see. I think if I actually go forward, I might have. No, I don't. Here, so you'll see. Basically, I'll show you maybe more details later. But the energy splitting between, let's see, these levels are roughly at a gigahertz. Let's say these two,
okay.
somewhere hundreds of megahertz to gigahertz. These two are up more around 15 gigahertz.
I see.
So it is. If it was much larger, then you're right. It would become difficult for us to control using our typical microwave hardware that we use in supercomputing. So yeah, you do have to hit a sweet spot for sure. But what's nice about these systems is that they're actually, I'm hiding a lot of the details of how the bias is tuned up, but we also have gates on these systems, and we can tune all these Andreev levels with gates. So honestly, I spent a lot of my time when I was doing these measurements just messing with the gates and the flux, trying to get the levels in a place where this kind of stuff would work.
I see. But basically, it's still limited in the region of superconducting gaps, right? But okay.
Yes, we will always be bound by that. It's always 44 gigahertz for aluminum anyway. But there are, I mean, I don't know. I mean, sorry, go ahead.
But for superconducting qubits, for example, like actually the frequency is more or less limited by the plasma frequency of the Josephson junction. But here you are actually can go really high up to like, well, it's really go to the energy level that go to the like the size of the superconducting gap, right? Or there's another some other thing limiting.
No,
okay.
that's the limit, I think. But also, I think that even in superconducting qubits, I think you could cook up a circuit where you have transition frequencies of interest that are pretty close to the superconducting gap like this. But also, I think it's just a convenience thing too, right? Like most of our microwave technology that we use is really geared towards the use of 0 to 20 gigahertz.
Sure.
It's just harder. It's just harder to find, boxes that go higher. They exist, of course, but yeah.
Okay, great. Thank you.
Sure. Okay, let's see. So yeah, final thing on the slide is just we're going to be using all 4 of these levels for these measurements. But the bottom 2 are qubit basis. I'm going to label those as up and down sub q. And then the upper states I'll call auxiliary states. And we actually need them because we use the microwave transitions from the lower qubit states to these auxiliary states. We use these both for detection and control, as I'll get into in detail. So yeah, let's get into how we do spin detection. So yeah, for those people that are familiar with superconducting qubits, this might look kind of familiar. Basically, what we do is we take our Andreev Spin qubit. It's in this same superconducting loop that I was talking about before, around which its current flows. And then we couple this inductively to a microwave resonator, which I'm showing here in maroon. And this is also superconducting. This is also made of aluminum. And yeah, like I was saying before, we use these transitions from the qubit states to the auxiliary states. And these transitions are in the order of 13 and 14 gigahertz. And so the way our readout works is it is circuit QED readout for those people that are familiar. It uses the dispersive shifts of the Andreev levels on the resonator, and you can basically understand this as level repulsion physics. So the resonator is sitting at around 9 gigahertz, and then there's these 2 transitions in the system at 14 gigahertz and 13 gigahertz. And so if we're in the down state of the qubit, you can imagine that this 14 gigahertz transition could happen. It exists in a way. And if we're in the up state, this 13 gigahertz transition could occur. And just the presence of these transitions is enough to virtually push on the resonator. They don't even have to really be excited. They just push like any level repulsion would, and they shift the resonator frequency slightly. And they shift it by an amount that we call chi, that we call this the dispersive shift. And this dispersive shift, because this transition frequency will be different in the 2 cases, this dispersive shift will be slightly different. And so for us, this dispersive shift is on the other order of megahertz, but it depends on this frequency detuning, this 14 or 13 gigahertz, like I'm talking about. And it also depends on the supercurrent coupling. So this is really the first example where we're using the fact that the Andreev levels carry the supercurrent in order to do something useful, in this case, couple it to a microwave resonator. Then what we do once we have this, the idea here is now because the resonator frequency depends on the spin state of the qubit, it'll be shifted slightly differently in the two cases. We can probe this by coupling a microwave resonator to a microwave transmission line. So all we do is we send in a microwave tone near the resonator frequency at 9 gigahertz, then it bounces off. But because the resonator frequency shifts depending on the qubit state, the reflection coefficient that it acquires, basically the amplitude and phase shift that it acquires, gamma, that's what I'm using for the reflection coefficient, it will be slightly different in the two cases. And so what we can see is if we plot the real and imaginary parts of the reflection coefficient, that's what I'm showing here, is we actually see 3 different responses. So this is now data from our experiment. And the 2 upper responses, these 2 blobs here, those correspond to the situation where the qubit is in the up state or the down state. But actually the brightest blob down here is what we call the ground state of the junction. And it's actually when no quasiparticle is present in the system. And we can look at these dynamics a little more closely by probing the resonator over and over and over again and doing what some people call a quantum jumps experiment. And so here I'm spreading out the Q value in time, this is microseconds, and you can see that in this example trace, the quasiparticle starts in the spin down state. After a while, it hops to the spin up state, stays there for a while, and then it hops to the ground state, which means the quasiparticle has left the junction. It's hopped out of the junction. And this is this parity switching that was mentioned before. Then, after a bit more time, another quasiparticle.
Oh, sorry. This one, did you apply any dry or just let it just tidy back?
This is just no drive. So this is just a background interaction of the qubit and the system with the environment. And so yeah, we can see these hops and the quasiparticles hopping in and out. Its spin is changing state, and we can characterize these rates, these transition rates, by 2 time scales. One is this parity lifetime that like you were saying is can be important for Majorana qubits, for example. So here we found it to be 60 microseconds. But actually, one of the advances that's been made in the field since this work is people have figured out how to stabilize the parity using essentially Coulomb physics. You can kind of make it so that it's preferred to have a quasiparticle in the junction, and they can stabilize it for milliseconds or seconds. So in a way, this problem of the qubit kind of popping in and out of existence has been solved. The second time scale is the spin lifetime, so how quickly the 2 spin states flip into each other, and here we found this to be 50 microseconds. So the spin lifetime, once we've dealt with the parity, the spin lifetime is basically like the T1 of the qubit. So we were pretty happy with this 50 microsecond value. It's competitive with superconducting qubits, which is interesting for the first devices that we're advocating. Still, we wanted to know why, like in superconducting qubits, we have different mechanisms for what can be causing the bit flips of the qubits. And so we wanted to know what was going on in this case. What is the qubit actually exchanging energy with when it undergoes one of these spin flip transitions? And so what we did was we measured the spin flip lifetime as a function of the phase bias across the junction. So this is basically the energy splitting of these 2 qubits, and also with an applied magnetic field that's perpendicular to the device. And so the color here is the spin lifetime, darker is longer spin. And then this gray region in the middle is a region that we can't measure the qubit. Basically, when the qubit energy gets too small, it becomes difficult to distinguish the 2 states in our readout. So we can't measure in here, but out in this region, farther away from 0, we can see a clear trend that looks kind of like this slanting thing. And what we realized was that this is very correlated with simply the energy splitting between the 2 spin states. So it looks like what we're seeing is that, and here the lighter color is higher energy. So it looks like what we're seeing is that when the Andreev spin qubit energy increases, the spin lifetime also goes up. And so this is a clue that tells us maybe where this energy is going, but it doesn't tell us for sure really anything. So what we wanted to do is compare to the existing spin qubit literature, so more conventional spin qubits, to see if there's anything to learn there. So the thing that makes most sense to compare to probably is single electron spin qubits. And in this situation, they actually see the opposite thing. They see that when the energy of the qubit goes up, the spin lifetime goes down. And in this case, this is understood to be due to phonons. Basically, the phonon density of states increases with increasing energy. So this is opposite of what we see, but maybe we thought this is just because the energy of these qubits is typically much larger than a gigahertz, whereas we're operating here, you can see from 0 to 700 megahertz. So we're operating a much lower energy regime. So maybe that's why. So we compared to a different kind of spin qubit called single triplet qubits, which are basically formed from 2 electrons and the single triplet states of those 2 electrons. And here, again, when the energy is greater than a gigahertz, they see that the spin lifetime goes down, again, due to phonons. But when the energy goes up at lower energy, below gigahertz, they also see the spin lifetime go up. And here, they understand this is due to nuclei in the system. So at first glance, this looks like maybe what's going on in our system. But unfortunately, we can't quite apply the theory of single triplet qubits because that theory that's been developed really only works for systems of 2 electrons. And we're working with really 1 electronic degree of freedom. So if we had to guess, we think that it's something to do with the nuclei in our system, but the theory is still yet to be done for exactly how that's happening. Okay, yeah, if there are no questions on the detection part and the lifetimes, then
I do, you know, I mean, in semiconductor quantum dot, the spin qubit, I mean, we usually talk about the material, which is sort of the limited performance of the spin qubit. For example, why people do it silicon, that's because it's a lighter atom. It has a smaller nuclear fuel, this kind of thing. But for this kind of Andreev spin qubit, essentially it's still it's still like a superconductor, which I think it's more like maybe as I talk to some of your group member, for example, if you make a nanowire, make it into a transmon, I think in that case, you think the highest coherence type you can make out of the nanowire would be the EO limitation. Like this spin, Andreev spin qubit would have is determined by the junction, the quality of the
but it's a different loss mechanism kind of, because if you were to make a gate-mon out of these nanowires, then they can couple to the dielectric loss, and that's typically what people think are limiting these gate-mons with these materials, like you say, probably because of the material quality. So fundamentally, it's because the electric field of the device, of the qubit, of the gate-mon, is coupling probably to charge defects in the substrate. So that's what's happening microscopically. But what's weird, like the Andreev, you're right, like the Andreev spin qubit is kind of superconducting qubit, but it's also kind of a spin qubit, and because it doesn't really have a dipole moment in the same way, or at least not nearly on the same level as a gate-mon. So, but it could still totally be charge defects potentially, but it would probably also be really the Andreev levels I think they are closer to the levels of a quantum dot in some ways. But I don't know. Do you happen to know if in semiconductor spin qubits that the charge defects can cause T1 problems?
I used to work on quantum dot, but I have been
really?
not in that kind of field for a long time. Yeah, I mean that's a good question. I wonder, when you talk about this Andreev spin qubit, I just you cannot think as a quantum dot because there's no sort of
it's kind of a quantum dot, but also kind of it's both.
Yeah. So how do you think we can figure this out? How do we study the mechanism that is limited? Do you have any idea?
Well, one of the things we want to do is use nuclear pure materials, and this is not only for the T1, but as you'll see, also for the T2. The T2 is much worse. And we're a little more certain that it is due to nuclei. So we want to see if just by using nuclear pure materials that we can improve the T2, and maybe that'll also do something to the T1. But I don't know. We probably also just need more statistics. This is just one device, and it's been replicated, I think, now in 2 other devices and other groups. But there hasn't been a very extensive study.
Okay. Thanks for the feedback.
Yeah, thanks for coming.
Okay.
Excuse me.
Yeah.
Yeah, I have one more question. So how about if you extend the parameter space, what is the behavior of the like the T1 or TS here?
You mean if we like try to go farther out in phase?
Yeah.
That's a good question. With this device, we weren't able to go farther because basically of the way the readout happened to set up in this device. But I think there is. So the short answer for this device is we don't know. But in my collaborators' lab, they have a new device where they're looking at this, and they've basically seen this behavior continue. Yeah, and I think we've still so far he's only seen that it's completely correlated with the energy, basically. So the energy at some point does turn back over and start going back down, and he also sees the spin lifetime go back down.
Okay. Yeah. Thank you.
Thanks. Okay, so we can detect the spin, but in order to use it as a qubit, we also have to manipulate it. And so again, we have these 4 levels. It turns out that in this experiment, we couldn't do a direct drive between these levels. Basically, by the way we built the device, there was a selection rule that kind of prevented this direct transition. But we could drive this transition from the purple state to the yellow state, and also this one. So what we did is we set up a lambda system using these 3 levels. And if we take these two, if we drive both of these transitions at the same time, and moreover, if we detune them a little bit, so they're only virtually populating this level, then we can use do spin manipulation via Raman transitions. So yeah, the idea is that if we start off in the down state and we drive this transition, the quasiparticle virtually populates the upper level before ending up in the up state, the pink level. So that was our approach. So how do we actually do it? So in the next couple plots, I'll be showing data in terms of probabilities. So in computing these probabilities, I'm taking this histogram and then I'm dividing the space into these 3 quadrants according to these dashed lines. And I'm just saying that if a point lands up here, I call it's in the up state. If it's in the middle region, it's in the down state. And if it's down here, it's in the ground state. So the first experiment we needed to do was to find these 2 transitions, just their frequencies. So the pulse sequence we did was we apply a microwave drive for variable frequency FD before reading out the system. And that's what this plot is showing. So you can see 2 features. There's a feature down here at 13 gigahertz where if we start in the pink state, kind of dips down a little bit. And this is a signature of us driving population out of the pink state and up into the yellow state. And over here, there's another feature which corresponds to the other transition, driving population out of the down state, the purple state, up into the yellow state. So once we had those 2 transitions, we could imagine doing a Raman process. So again, what we want to do is we want to apply 2 simultaneous drives. So I'm going to use this striped Gaussian to indicate simultaneous drives of a certain pulse shape. And then we want to apply these drives detuned from these transitions. We're going to choose a positive detuning on both of them. And then we're going to sweep them around in these regions that I'm showing here in order to search for this Raman process. Before we do that, there's one final ingredient we have to add, which is that we need, if you look in the background of this plot, you can see that if I don't do anything to the system, the equilibrium population of the upstate and the downstate is about the same, which means that if I drive a Raman process between them, which shuffles population between them, I'm really not going to see much of a change because that process is just as good at driving population from the purple state to the pink state as the pink state to the purple state. So I'm not going to see much. So what we do instead is we start the whole pulse sequence with an additional readout pulse and require that we find the system is starting in the pink state, the up state. So we're post-selecting here in these measurements. So this is what that experiment looks like. We're sweeping again this frequency of these 2 drives. We're starting in the up state. You can see the background color in this plot is mainly dark blue. And this probability, this color here is the probability of finding the system in the down state. So you can see that most of the time we're staying in the up state and we're not switching to the down state. But then along this diagonal, there's this white stripe. And this is the Raman process showing up. We're seeing population transfer to the up state. And the reason it's a diagonal line like this is that if I increase the frequency of the pink drive, then I also have to increase the frequency of the purple drive by a little bit in order to make sure that I'm meeting this Raman resonance condition with this basically this black dotted line up here. We can look a little more detail by looking at the full histograms for data on and off of this Raman resonance feature. So in the black region, again, you can see here that we're only seeing population in the upstate mainly. There's some population in the downstate and the ground state. This is just due to transitions that'll happen naturally during this pulse sequence, just due to interactions with the environment. But then on the Raman feature, you can see that there is significant population transfer to the downstate. So yeah, this is great. This is what we wanted to see. We have population transfer, but it doesn't necessarily tell us that the population transfer is coherent, which is what we need in order to use this as a qubit. So to do that, we're going to play a very similar pulse sequence to this, but now we're just going to vary the amplitudes of these two Raman processes, parking on resonance with the Raman resonance. And so that's what we're looking at here. White in this plot corresponds to not much, let's see, it corresponds to mainly spin up. And so this means that we haven't had much population transfer. And this makes sense. Basically, this is telling us that when either the amplitude of the up drive or the down drive is 0, we don't activate this Raman process and we don't see any population transfer. But if both are on at the same time and roughly the same magnitude as we go out along one of these diagonals, for example, you can see that these oscillations develop. And this is a sign of, these are basically Rabi oscillations of this Raman process. And we can simulate this to make sure we have a decent idea of what's going on in the system. And in the simulation, we have some various free parameters that are basically the matrix elements of these drives, these various transitions. And also, this is definitely in detail, but there's a kind of a detuning from this Raman resonance whereby these two drives are kind of missing each other and not quite on resonance with each other. So once we have these Rabi oscillations, we can measure the coherence time of the quasiparticle spin. And so we did standard Ramsey echo measurements in order to probe this. And we found that the Ramsey time was around 16 nanoseconds and the echo time was around 50 nanoseconds. And these numbers are quite low. They're quite a bit lower than the spin flip lifetime of around 50 microseconds that we were looking at before. And so I think this is one of the big questions facing Andreev spin qubits. Why is this time so low? So what was curious was that we found no dependence on any of the gate voltages or the flux, which if anybody's familiar with, for example, flux qubits, in flux qubits, if you operate at a flux sweet spot, then you're first order and sensitive to flux noise, and you usually see an increase in T2. We didn't see anything analogous to that in this system with the flux or the gate voltages. Really, the only clue that we could find was that, and this is where actually these pair transitions come back in. We were talking a little earlier about these pair qubits. We found that those qubits actually had better T2s. They had worse T1s, but better T2s. And the T2 for these things was about 500 nanoseconds. And what's interesting about these pair transitions is that they're in some sense spinless. They don't couple to things like magnetic defects, excuse me, or other things that might shift a spinful level. And so what this tells us is that because this is order of magnitude better than the spin qubit, tells us that we're probably limited by something that couples the spin. So they're nuclei, paramagnetic impurities, maybe phonons plus spin orbit or something. But what's also interesting is that there's this old work on so-called spin orbit qubits that, in my opinion, are kind of the closest cousin of the spin qubits to the Andreev spin qubit. They also use spin orbit coupling in a similar way that we do. This thing is also limited to about 15 nanoseconds, and they were pretty sure that they were limited by nuclei. So we think in the system that we're also limited by nuclei, probably. And so this is why I was saying earlier, I think one of the next things that needs to be done is to investigate these systems with some nuclear spin-free materials.
In your previous PI or the T2E, right? The ground state recited state you are referring to. How long is that? How long was that compared to the
in the pair qubit or the spin qubit?
Pair qubit, yeah, pair qubit.
What was like the effective T1 of the pair qubit?
The
Is that the
effective T2. I mean,
So the effective. Oh, sorry. This T2 is an echo.
This is
This is an echo value. This is echo.
Mhm.
Yeah, sorry. Yeah, that should be an E there. Yeah.
Oh.
Yeah. So the two numbers to compare are probably this 500 nanoseconds with this 50 nanoseconds.
Mhm. Okay. Maybe. Okay.
Excuse me. I have a question regarding your operation of coherent transfer. So in here, you overlap these two drive pulses. But I remember I ever read some article mentioning that if these two pulses, if would introduce in is a slight different time, small different time delay, then the transfer probability will be higher. So is that correct in your system? Or
yes, that could work here. So I think, are you referring to, there's a protocol called STIRAP, stimulated Raman by adiabatic acid or something like that? Does that ring a bell? Maybe, but it's basically what you say. Yeah, if you introduce a delay between two pulses, then you can, what it lets you do, and it is powerful. It lets you so in all these experiments, we had these two drives detuned from this level. If you do this, where you delay them a little bit, then I think this is maybe what you're referring to. If you delay them a little bit, then you can instead drive on resonance with this level, and so you can go much faster. You can do the gate faster.
Okay.
It's a complicated. The pulse sequence is more complicated, but yes, you're right. In principle, in any lambda system, it should work to do that. We actually do have a theory paper investigating that, but we never actually did it in experiment.
Okay. So could you remind me again, how long is your driving pulses in here?
Yeah, I feel like I don't actually have that on here. That is important information that's missing. That's, if I recall correctly, it's approximately 50 nanoseconds. So that's one of the reasons that these oscillations don't look very good, is because these pulses are on the same level as the T2, right? And as soon as you have that, you're just not going to get a very good coherent transfer. Yeah.
Okay, thank you.
We found that one interesting thing was that when we tried to go faster in the system, we found that the drives started blasting the quasiparticle out of the junction. So it would basically just destroy the qubit if we tried to go any harder. So that's kind of what was limiting the speed for this particular set of measurements.
Okay. Yeah.
Thanks.
Thank you.
So sorry, I have two kind of questions. First, I mean, in the very beginning, you mentioned that, well, the direct driving from the purple to this magenta state is forbidden. So this is due to what? You need to flip the spin, or what?
Yeah, it's so in the appendix of our paper we go into more detail on this. But it's interesting. It has to do with it's related to spin, flipping the spin, but it also has to do with it turns out basically that if the system is perfectly mirror symmetric, like if you imagine drawing, like slicing the nanowire with a plane down at the length, if it has a mirror symmetry plane, then there is a selection rule that forbids switching between those two parity sectors. And it turns out that these two eigenstates are in different parity sectors.
I see.
But in our drive, the way we set up our drive, it's also along the nanowire, so it doesn't break this mirror symmetry. But there has been work since our work that uses a side gate that comes in, and this does break the mirror symmetry. And so then they actually can drive directly between these two states, and they can get much better manipulation than this. So now there is data out there with much cleaner oscillations than what we were able to show.
I see. But isn't that this will be related to your previous topic, saying that for the T1, actually then the loss channel coupled to these two state actually is not, I mean, it must be a mechanism that you need to break this symmetry, break this selection rule.
Yeah.
Otherwise, this shouldn't happen.
No, you're right. It has to be the case. Yeah.
Yeah, so maybe I'm not sure if phonon can do that, because it looks like I'm not sure. Yeah, but it seems to me that you can use this selection rule to eliminating some of the loss channel because they may not be able to release
to break that.
So,
yeah, that's true.
Mhm.
Yeah,
Okay.
that's a very good point. I think a systematic study of that where you're actually breaking this mirror symmetry in different devices could be definitely, as you say, useful in understanding where this spin flip is coming from.
Yeah. The second one is for your T2 measurement. You have like T2 echo is looks to me is longer than the Ramsey. Does that mean that the noise is if this is true, then does that mean this the phasing noise actually has kind of like a frequency dependent because your echo more or less it's actually have like a higher it's like a because echo is like a sensitive to a noise window that is
higher
going
frequency.
to higher frequency.
Right.
And
That's right. Yeah.
maybe did you try, for example, the CPMG? It's like you put some more.
We didn't. But a follow-up paper also investigating Andreev spin qubits did, and they basically found if I recall correctly, a 1/f scaling of the noise. Yeah, like as you say, you can basically do CPMG to look at noise spectroscopy, to do noise spectroscopy. And I think it was or something like that. It was or some kind of polynomial scaling, something that looked kind of like that. Which yeah, I don't know. I find that this is when I first started looking into this, I was quite confused by this in the context of the nuclei, because there are some references out there that say that nuclei have very slow dynamics, and as such should be very echoable. So like you would expect an even larger ratio of the Ramsey to the echo. But then there are other references that say that this is possible to have to still for the nuclei to still have relatively fast dynamics that can't be completely echoed.
I see. Okay, good. Thank you.
But yeah. Thanks for your questions. Okay, let's see. What time is it? How much time do I have left? I guess we're at the hour, so I can stop here if I need to, or I think
it's okay. We can go if you don't mind. We can go. We can let you finish. You know, we are happy.
Cool. Yeah, I just have only two more slides on the subject. So basically,
I think you can just finish.
Yeah. Okay. Great. Thanks. So since this work, there have been several other groups working on these devices, and they've seen some pretty cool things. But I want to focus on one advance that I think is really cool. And one of the things that I think Andreev spin qubits can add, not to superconducting qubits, but actually to spin qubits, because one of the problems with spin qubits is scalability. So kind of the issue is that for these spin qubits, for each spin qubit, you need a ton of gates to come down into the device. And at a certain point, if you have a very densely packed array of spin qubits, it becomes challenging to imagine like actually getting all of those gates and control circuitry into the device. So what people imagine doing is instead having smaller grids of qubits, so as depicted here, and then these separate little processors are connected via these long-range qubit couplers, as they're calling them here in this reference. And so then the question is, how do we actually make these long-range qubit couplers? And the thing that's been the most popular so far in spin qubits is to try to borrow from superconducting circuits and to couple spin qubits via a superconducting resonator bus. And so this is a technique that was originally used in superconducting qubits and is still used basically to make 2-qubit gates between two superconducting qubits. And the idea here is basically the same. We have two spin qubits at different ends of this resonator. There's a capacitive coupling from the qubit to the resonator, and then the resonator kind of mediates this interaction between the two qubits because they're both interacting with it. And this kind of idea has been around for over a decade now, and there's been a lot of progress on it, but they still haven't managed to get a 2-qubit gate between these two qubits. And really the problem is that this capacitive coupling is just really small, and it's limited by the dipole moment of the electron, which is ultimately set by the size of the dot. And the dot can only get so big. So they've played all kinds of tricks using high impedance resonators and all kinds of stuff. And finally, just this past year, they did manage to get something that looks like coherent swaps between the two spin qubits, but it's still not a gate between them. And so this is where I think the Andreev spin qubit can actually help quite a bit, because its coupling is not limited to capacitive coupling. We can use the supercurrent coupling instead. And it's not limited to the size of the junction in the same way that these qubits are limited by the dot size. So as a cartoon, for example, you can just imagine embedding 2 Andreev spin qubits in one superconducting loop. And so these pairs of black dots are supposed to be Cooper pairs traveling around the loop. Basically, the current mediated by this spin qubit can flow around the loop and talk to the other spin qubit, or equivalently, these two currents mediated by the 2 spin qubits can talk to each other. And so there have been 2 experiments this year that have demonstrated things to this effect. So this first work was actually not using spin qubits, but using these pair qubits that we've talked a little bit about. And here they were using inductive coupling. They inductively coupled 2 different pair qubits to different ends of a resonator. And then what they were able to see is this data isn't the clearest, but you can see that there's some avoided crossings in the spectroscopy here. This matches roughly with their theory. So the coupling that they're looking for is basically just the avoided crossing between these lines in this plot over here. Probably the one that I'm the more excited about is this other work from Delft using 2 Andreev spin qubits, and it's kind of much closer in nature to this cartoon that I've drawn over here on the left. And so what's happening here is that they have 2 Andreev spin qubits. They've embedded it in this circuit with a tunable squid, a third tunable junction here. And this junction kind of controls the degree to which these 2 qubits are coupled to each other. And it creates a coupling of the form in the Hamiltonian that looks like sigma z of one of the qubits times sigma z of the other qubit with the strength j. And then they can probe this by, if we look at this level diagram here, you can see how this probing works. Basically, we have the 4 computational states. And then there are 2, we're going to look at kind of 2 transitions we can imagine. So there's the blue transition. And so this is basically the transition of qubit 2 when qubit 1 is in the spin down state. Or we could look at the transition of qubit 2 when qubit 1 is in the spin up state. And these 2 transitions will have a difference in frequency that's equal to 2 times j, the coupling between them. And so what they're doing here in this experiment is they first apply a pulse between these 2 levels to create a kind of a mixed state of these 2 levels, and then see if they can see a splitting in spectroscopy. And that's exactly what they see. So they see these 2 peaks, and they're separated by this value that we know to be 2j, basically. And so here they're seeing a coupling, a j, on the order of, I think it's here about 200 megahertz. And so this is way, way larger than any kind of coupling that the folks in normal spin qubits have been able to achieve. I think they're, at the very most, they've been able to achieve 10 megahertz. So yeah, well over an order of magnitude beyond what's possible with conventional spin qubits. Yeah, so hopefully there will be more exciting developments in Andreev qubits in the year to come. But yeah, I think with that, yeah, I've told you about our detection, our manipulation. I'll quickly flash the photos of all the wonderful people who helped me do this work, particularly Michelle and Vala. Yeah, thanks for letting me run over. And if anybody has any more questions, I'd be happy to take them.
Yes, thanks for the great talk. Yeah, I think from the interaction during your talk has already said that this talk is very interesting. Yeah. While we don't want to hold you for too long, is any other question people want to ask? Okay.
Here I have a question. I think is regarding the selection rule Yanxiang ever mentioned. There's transition forbidden from the lower 2 levels. So when your measurement on T1 indicate that the relaxation time increase as that level increase. So I wonder if that is actually we needed to seek any symmetry breaking interactions so that we could explain that.
Explain that. Yeah, I don't know. I mean, I guess I think the previous point was a good one. That I mean, if we can't, well, I don't know. I guess it's the symmetry. The symmetry protection thing could also be something very specific about the way our drive is set up. No, but no. I mean, that whatever the interaction is, I guess it does. If the so here's a schematic of this mirror symmetry that I'm talking about. Basically, you can imagine a mirror running down the nanowire. And so you can see that, for instance, the gates partially break the symmetry of the presence of them. I guess I don't know. I think if that mirror symmetry is present, and for the record, it is always broken on some level by the gates or just material defects or something. But if it is present, then whatever a thing that couples the two sectors does have to break that selection rule. But maybe it's easy to break. Maybe, yeah. I mean, you can imagine, like, for instance, just a defect that causes a magnetic field in this direction, right? That'll automatically break the mirror symmetry. So maybe it's not a very powerful symmetry.
Yeah. Okay, thank you.
Okay. I have a maybe very naive question. So Max, in all your paper, you have this kind of a quarter wavelength, this resonator. What is the point to use that kind of structure? Is there any particular reason?
Of using a quarter wavelength?
Yeah. And also quarter wavelength.
I mean, so I guess we need quarter wavelength is nice for us because quarter wavelength means that one end of the resonator will be shorted to ground, and so that'll have a maximum in the current, and that's where we would want to put in an Andreev qubit because that's where it'll have the strongest coupling. But then the other end of the resonator will have an open, so that means we can capacitively couple with a readout line or something. But it's definitely not critical. You could use other kinds of resonators if you wanted to.
Quarter wave, in your case, you have you have two open end, right? But I know it's getting thinner as an approach to the RF screen.
Yeah. Well, yeah. Let me see. Do I have a picture of the device? I don't have a picture of the device in these slides. That's a mistake. Yeah. Oh, but the oh no, here it is. So it's kind of a quarter wavelength resonator. It's weird. It's really more of a half wavelength resonator, because we're using, you see we have these two ports, and so we're using a 180 hybrid to create a differential microwave voltage here. And so there's a plus V here and a minus V here. So if you imagine taking this red thing, imagine taking the red resonator and splitting it and like unwrapping it, going like this with it, then this end is kind of like plus V and this is minus V. So it really looks more like lambda over 2 than lambda over 4, and the Andreev qubit is sitting in the middle. You see what I mean? So that's it's a weird resonator. So the reason the reason this design is like this is because we were kind of obsessed with symmetry. We wanted a very symmetric structure to avoid any like unwanted couplings. But honestly, I think we went overboard. I don't think it's necessary to use this kind of device.
I see. And when you apply magnetic flux, do you use external field or do you have a flux line? I can't recall.
No, it's an external field. We don't have a flux line.
I see. Okay, gotcha. Yeah. Okay, thanks. I mean, just a minor question that I've been having for a while. So.
Yeah, that's right. This device is weird. I don't know. There's no particular reason it needs to be so weird.
Okay. Yeah. So, any other question that people would like to ask? Yeah. Okay. If not, I think Max, I think you are doing a very interesting topic before, and even now when I visit you, you introduce a lot of bosonic qubit, which I consider you to be sort of a rising star. Maybe in the future you also become quite because you do master in different direction, which is really good. So hopefully we will be able to see you in the future. But appreciate your talk, spending tonight.
Yeah, thank you very much for the kind introduction, and
thank you for all the professor. Yeah, thank you for all the professors to join and give a nice question. Okay, thanks.
Thanks for inviting me.
Have a good day.
Bye, everybody.
Yeah. Okay.
Thank you.
Thank you. Okay. Bye.